Hello everyone. So in this section we're going to explore a graph of logarithmic functions and we are going to analyze their graph and go from there. We're going to basically talk about all the important characteristics of logarithmic functions. Okay, to start, let's consider the function f of x equals 2 to the x. This is exponential function and we want to find its inverse. Okay, so that's what we want to do. And remember that to find an inverse of any function, all you have to do, you switch x and y, all right, and then you rewrite. So here is the first step. I switched x and y, so that's what happened right there to find the inverse. Now the idea is that you're going to continue and solve the new equation for y again. That's how you come up with the equation of the inverse. Now we have to use logarithmic laws to do that. You will change this into a logarithmic form. Okay, so that's what that is when you take the log of both sides. So basically, what would that be? Well, that would be log of base 2, the value is x, that will equal to y. Okay, so the f inverse of x is log of x base 2, which is what we call that to be y. So here is the very basic parent logarithmic function, which is the inverse of y equals to 2 to the x, the parent exponential function. Okay, so these two are inverse of each other's, and we already know how to graph exponential function. Now we're going to go ahead and explore graph of the logarithmic functions. Okay, so I have graphed y equal to 2 to the x, that's the parent exponential function, and the red graph is right there. And I just want to make sure that you see that I just interchanged x and y to get the inverse. And if I do that, that means that every coordinate on the original exponential function will have their x and y values interchanged. So if this was 0, 1, the graph that we're going to end up getting, graph goes through the point 0, 1, 0. Okay, so and every single other point. So this coordinate here was 2 and 4. The chances are for sure 4 and 2 will be on the graph of the inverse. Now I left it like that so that you can see Desmos does this for you, but I also have wrote here, typed in the actual inverse function after solving the top one for y, which will end up being the same. It should be. So let's give it a try. So here is the inverse of the exponential function, which is right here. And after we have done our manipulation using the log laws, we came up with the expression y equal to log of x base 2. But these two graphs, x equal to 2 to the y and y equal to log of x base 2, they're the same. They are the same. They should be the same if I've done this correctly. So when I click on that, notice that they are the same. Becomes a green graph right on top of the blue graph. So and here are the points where you know that the values are exactly what we talked about. The x and y coordinate of the exponential function has been interchanged and switched, and now you got these coordinates, and sure enough you got one coordinate 1, 0, that's your x-intercept. 4, 2 was 2, 4, so that's been interchanged, and so as any other points that you can think of. Okay, on the original exponential function now has been switched the x and y coordinate and it become part of the inverse function. So that is a general look of the logarithmic functions. Now couple of things we need to talk about. Number one is that notice that the exponential function had a y-intercept. That was the y-intercept. Didn't have x-intercept because there was a horizontal asymptote. That was the x-axis. The equation of the horizontal asymptote for the exponential function was y equal to 0. But for the logarithmic function, it is the inverse of the exponential. Notice that there are no y-intercept, but there is x-intercept. And also, it makes sense to see that the asymptote has been changed to a vertical asymptote. It makes sense. Now, x equals to 0 is a vertical asymptote for log. So, logarithmic functions have vertical asymptotes. Exponential functions have horizontal asymptotes. All right, so that's basically it. And based on what we do with the function transformation, as we have done this with polynomial function, with the function transformation, with the exponential function, or any other functions, when we move, we do the transformation, moving it left and right, or moving it up and down, and then the expansion compression factor for all of that, vertical and horizontal, they exactly apply to the logarithmic function the same way as they applied to all other functions. Okay, so here is the graph. Again, I just pasted that graph in here. Just write down a few characteristics of the logarithmic function. The green graph is a logarithmic function, log of x base 2. The x-intercept is at 1, 0, and then is a vertical asymptote that it is the basically the y-axis, but the equation of that is x equals to 0. And then I want you to also remember that when you're doing the inverse, it's the reflection. It's a form of reflection over the diagonal line y equal to x, and that's how we get the two as a mapping. Okay, so you flip that over the y equal to x. Either one of the two functions, exponential or logarithmic functions, they map each other. All right, and that's basically it. There are no remember, no y-intercept for the logarithmic function, no y-intercept, and that's basically it for the parent function of a logarithmic function. So the last thing we need to talk about is domain and range. Just like any other function, we need to talk about that. And look at the graph, and you can see that the x values they have to be greater than 0, and then everything else will apply, and all the number. And then range goes up and down basically forever. So y belongs to all real number. That's a typical domain and range. Of course, it changes depending on the transformation of the function. And then the last piece that I need you to pay attention to is that for any y equal to log of x base b, so now base is b cannot be 1, and b has to be greater than 0. So this is a very important part. Okay, so remember the restrictions in here, and that's part of the base, and of course we know that x has to be greater than 0.